So what this is going to lead us to, and what we're doing now is going to lead us to, is this, the fundamental theorem of statistics. And in statistics, our fundamental theorem is what we call the central limit theorem. And we also refer to this as CLT. CLT. And it states that when n is sufficiently large, well, sufficiently large in particular in terms of our sample size, when n is greater than or equal to 30, is sufficiently large, the sampling distribution of the sample mean, remember the sample mean is what we call x bar, will follow, and here's the key thing, it's going to follow an approximately, it's not fully normal, but it's approximately normal distribution with the following parameters. So we're going to establish parameters. Remember, the parameters are the true values of the distribution. And since we're talking about the parameters for the sampling distribution of x bar, remember x bar is the sample mean, we can say this, and we saw this from the example, that x bar follows a normal distribution with a mean equal to the mean of the population. We call the population mean mu of x. And a standard deviation equal to what we now call the standard error, which is going to be the standard deviation of the population divided by the square root of n. These are what we call our parameters. And remember, parameters are true values. They're true values. And because you have this approximately normal curve, there are two parameters for the normal curve. Every normal curve has a mean where you have a center at, and then it's spread out by the standard deviation. The standard deviation here is now called the standard error. And we call it standard error because this term up here is technically called the standard deviation. But the standard error itself is still a standard deviation. So this is just still a standard deviation. But we refer to it as the standard error. And so we can use all of this when our sample size is sufficiently large. And remember, we call it the central limit theorem. But if you go back to our other example, our sample size was only 2, and we still got the exact same results of a normal distribution. Well, it turns out that when the sample size is not bigger than 30, so when it's less than 30, CLT can still be applied if the parent population from which the sample is drawn is already normal. Meaning that if you draw a sample from a normal distribution, the sample itself will also be normal. So what this tells me is that when n is less than 30, I can still use CLT as long as that it is stated that the population is normal. And so all of this really means, and here's what we're going to do, these two examples are going to show you what we're doing this, is we're going to establish the parameters for a normal distribution. So example 1 says, David's iPhone has about 10,000 songs. The distribution of the play times for these songs is heavily skewed to the right, with the mean of 225 and a standard deviation of 60 seconds. Describe the shape of the sampling distribution for the sample mean for an SRS of size 100. When it talks about describing the shape, this means what are the parameters of the distribution? And notice that it says that this distribution itself already starts out, the parent population, as we're going to call that, is heavily skewed to the right. Well, it turns out that if you look, anytime you see a sample size, anytime we have something with a sample size, we want to verify that it is bigger than 30. So we have a sample size here, SRS, in case you forgot what that means, it's called a simple random sample. Remember, a simple random sample is just when every possible element in the sample has an equal chance of being selected. So basically like putting names in a hat, drawing them out, or numbering everything in the population and drawing them out. But you have an SRS of size of 100. This 100 is significant. And that's the first thing we're going to start doing in this problem. We're going to identify the sample size. So here n is equal to 100. And because n is greater than or equal to 30, which is this what we're looking for. We want a sample size bigger than 30. We can say by CLT. The other thing we're talking about, we're describing the sampling distribution for the sample mean. And remember, the sample mean is called x bar. So we're saying x bar, because of CLT, x bar now follows a normal distribution with a mean equal to the mean of the population. Well, the mean of the population here is 225 seconds. And a standard deviation equal to the standard deviation of the population divided by the square root of the sample size. So in this case, that would be 60, the standard deviation of the population, divided by the square root of 100. And then we can just simplify that. 60 divided by 100, the square root of 100. The square root of 100 is 10. 60 divided by 10 is just going to be 6. So basically we have parameters that say the mean of this curve is going to be at 225. Standard deviation is going to be at 6. Notice that when we look at one song, or we look at the distribution of the time played for one song, it's 60 seconds for the standard deviation. When we look at a group of 100 songs and find their mean, though, it's only going to be, standard deviation is only be 6 seconds. The reason that this is occurring is because the sample is getting large enough to mirror the population. And remember, standard deviation is a measure of variation from the mean. Therefore, as you take more things that look like the population, you have more information, the variation should start to decrease. So your standard error should always be smaller than the actual standard deviation of the problem. So here what we looked for was a sample size bigger than 30. We got a sample size bigger than 30. We can use CLT, and we stated that we use CLT. X bar was approximately normal with the mean of 225, a standard error or a standard deviation of 6. In example 2, it says the customer care manager at a cell phone company keeps track of how long each helpline caller spends on hold. The distribution of wait times is approximately normal with the mean of 12.8 minutes and a standard deviation of 7.2 minutes. Describe the sampling distribution of the sample mean for an SRS of size 16. So again, I'm describing the distribution, and it's the distribution of the sample mean, or X bar. But this time when I look at it, my simple random sample is size 16. So here n is equal to 16. Well, that's a problem because n is not bigger than 30. But if it's not bigger than 30, we go to the second condition that we can check, and that's that it comes from a normal distribution. And notice here, it tells me that the distribution of wait times already is approximately normal. So because of this, because the distribution is approximately normal, by CLT, X bar, the sample mean, follows a normal distribution with the mean of the population. In this case, the mean is, the population is 12.8. And a standard deviation equal to, or a standard error equal to the standard deviation of the population, which is 7.2, divided by the square root of the sample size, divided by your sample size here is 16. And we can clean that up. 7.2 square root of 16 is 4. So 7.2 divided by 4, that's 1.8. So this new standard deviation, or the standard error, is actually 1.8. And notice that it decreased in size.